Hi folks, so the next thing up is something a little bit different. This is a JBL Yuri 6260 stereo power amp. I believe it's rated 200 watts a channel, and it came from, who else? My buddy Steve. I'm basically on retainer with this guy, but he said he had sold it, shipped it, it got damaged in shipping. So we're gonna have to take the bottom and top covers off and see if there's any damage before I fire it up. And when I do, of course, I'll do it on the dim bulb tester. These are old school, big iron, heavy linear power amps. And not much else to say at this point, so let me get the covers off, we'll see what we got. All right, got the bottom top cover off, and I don't see anything wrong. There's no damage. I tapped on the board. Nothing cracked, nothing broke, but when I go to test it, and it came up okay in the dim bulb tester and it comes out of protection, I'm only getting one channel. It looks like the left channel is okay, channel B or the right channel is not. So I'm gonna have to take a look here and see if we can figure out where the problem is. All right, so what I'm gonna do here is I'm going to turn this on, and I check the base of the outputs on channel A and channel B, and it looks like the channel we're having problems with isn't actually biasing the outputs on. I'll show you what I mean. So it's on, clicks out of protection, and if you look at this channel, we get about, I'd call that 5.1 volts at the base, and if you look at the other channel, we get 0.36, and that's not enough to turn that transistor on. So we may have a bias issue. Let's see if the bias does anything here. No, it doesn't. So we're gonna have to see why that's low. We may be getting signal up to there, but that transistor is not turning on. In fact, let's see what happens when we put a little more signal in. It's 10 millivolts. Yeah, you see how, of course you didn't, because I don't have the camera pointed at the scope. So you see how we have a little signal there now? Okay, 200 millivolts, and it just kind of pops up and goes down. There's definitely a problem with that channel, so I'm going to print the schematics out. We're going to take a look at this. We've got a lack of bias causing our problem here. Now, at the output here, we should have 0 volts. And although no voltages are given on the schematic, we can extrapolate what they should be just by gauging what we should drop across our emitter base junctions all the way back to here. So output, ideally 0 volts, no offset. And then at the base of the outputs, we should have anywhere between 0.5 and 0.6 volts, somewhere in between those. And as you saw, we got about 0.3, 0.4, somewhere in there, I don't recall. Good thing about stereo amplifiers is even with no voltages given, you can just compare the good channel to the bad. But this rule of thumb should give you a ballpark idea of where we should be. So we should have 0, 0.5, 0.6. Here we should have 1 to 1.2. And then we get back here to our differential stage. This amplifier doesn't have any offset controls, but I believe they're using this op amp down here as a servo. They're tapping off the output here. The input to the signal input to the output stage also comes through this op amp here. This is 1/4 of a quad op amp, a 14-pin dip package, and the output of the op amp feeds into the input side of the differential, and in your negative feedback amplifiers, your output also feeds back into the other side of the differential or long tail pair here. So we got problems, as far as I could tell, back in here somewhere. Could be our op amps, could be a problem in the output stage here. I went in the house and I left this on. When I came out, it was in protection, and I had 60 some volts on the output stage here. So I turned it off. When I let it cool down a little bit, it went back to the symptoms we were seeing. But anyhow, going to go through here, and we are going to write down what our good voltages are, what our bad voltages are, and you'll see it points back to this area here somewhere. Before I go in and take these voltages, I want to talk a little bit about probe extenders. Now, I have used these for a while. I bought the inexpensive ones on Amazon, but they seem to have too much flex, and they were a little loose on the probe after a while. So I bit the bullet and bought the genuine Fluke. They were a lot more expensive, but I think they were worth it. However, as you can see, they're insulated all the way up to the tip. You have to keep an eye on them, because over time you will find that it wears away a little. The heat shrink gets a little frayed. You pull off the excess. Now you have more tip exposed. And I'll show you a picture I took under a microscope of this and the new one. And my old cheap ones I decided to re-insulate, which also had the added benefit of giving them a little more strength. And I have only the tips exposed on this. I just stripped some wire and used the wire strippings to insulate these. But very important, you have something like this, because if you use just a bare probe like this and you go to probe some output transistors like we have in this amplifier, all it takes is one slip to cause massive damage to the output stage. Look, we've all done it. I certainly learned the hard way, the way I seem to have to learn everything. But do yourself a favor, get some good quality tip extenders, get some spring hooks, just get any kind of probe extension that will make probing safer and less eventful, if you will. All right, I'm going to probe good channel, bad channel. I keep a couple of colored pencils here. The green, I will notate the good channel on the schematic. The red I will use to notate the bad channel on the schematic. And this makes it easier to trace your way back and find out where the root cause of your trouble is. So I'm going to turn the amplifier on. We're going to probe first good channel, then bad channel. And we're going to start. We already know what the output is, because when it's out of protection, I have it currently plugged into two of my bench meters. So we know what the output is. So we're going to probe first one of the bases, good channel, bad channel, and then we're going to go back to the driver, check the base of that, good channel, bad channel. I'll notate the schematic as we go along, and it points to the front of this where the differential is, but I'll show you my methodology for this. Basically is what I'm doing. Amp on, clicks out of protection. So good channel, base. We have 0.51. Okay, so I'm going to notate that. 0.51, bad channel. 0.42. Okay, now we're going to go back to the driver. So that's going to be Q17 and Q8. So Q8 is our good channel. We have 1.1. And I'm only doing the NPN side because the malfunction seems to be symmetrical here. And our bad channel, let's see, this should be here. We have 0.83. Okay, and that takes us back to the front. So I want to talk a little bit, I'm going to put the schematic up here. I'm going to talk a little bit about what's going on in the front here. Now, as you can see on the schematic here, we do have a bias adjustment, but we have no offset adjustment. And if you look at my meters here, I'll turn the amp back on. I have the outputs plugged in. And let me raise it up a little, get a little closer. Amp on, out of protection. So these are output offsets. So you can see they're very low. So I believe that they're using that op amp as a servo to keep the offset low, and they're also feeding the signal through it. Now, the digits jump around a little bit, but you can tell this is microvolts. This is millivolts, extremely low amounts of offset here. So I believe that that's what they're doing with this op amp, is they are using the op amp as a servo to have a closed loop system that keeps your offset exceptionally low. Well, I found something of interest. I went back on the negative side and I just checked the base of the drivers, and good channel. We expect around negative 1.2, we get negative 1.1. But on the bad channel, we get positive 0.83, which is exactly what we get at the NPN side, or the positive going side. So I thought, oh my God, we have a shorted bias transistor, emitter to collector. But measurements show that this transistor is good. So I'm going to go back and going to focus on this area here and see where the problem is. I also want to take a look at the servo input versus output. So I'll take some measurements and we'll see what we get. All right, so what I decided to do, since I have bad voltage here, and I don't think it's the op amp, because I popped in a TLO 7.4, which is a pin for pin equivalent. I think the 7.4 is a low noise JFET, and these are just standard JFET, but it didn't change any of the symptoms. So that's when I began to focus my attention up on the differential inputs, and all four of these tested good, and this tested good. This one did not. And I was just going to unsolder it when I popped the amplifier up on its side, and it looks like it's been replaced before. Let me move the amp and show you what I mean. So 31 is right here. And if we look back here, and I'm going to move the camera and shine a little bit of light in there. See right here, somebody soldered a piece, somebody unsoldered and replaced that. So we're going to want to take a look at that and see what's going on and clean this area up. But I believe this is where our problem is, and I'm a little curious why it went. But let's see if they used the original replacement and, like I said, clean this all up. I pulled transistor Q31 and it checked good out of circuit. But I did find that mess underneath on the PCB from where a trace had broken. So I cleaned up everything. I soldered a fresh wire in, and I put another wire going to the base, and things are looking up. When I check it now, and I'm going to turn it on, and we're going to check the base of Q13 and the base of Q17. I extrapolated negative 1.2 volts. Good channel is negative 1.1. Bad channel was positive 0.3 at the base of Q13. So let's see if we can get to that and see what we get. See if we can get the meter where we can both see it without too much glare. It looks acceptable. And I want to find Q13's base. All right, negative 1.06, much better. And if we look at 17's base, yeah, positive 1.05. So things are looking up. I'm going to check the bias on that channel, and I got to let it discharge because you got to dig into this thing. I didn't mention it, but we have all the output transistors mounted here, and underneath there's another set mounted the other way. You can't quite see the pins coming up through the circuit board, but I'm going to have to tap off an emitter resistor off of an NPN to PNP to check that. And we're going to want to let this discharge, make sure I don't short anything when I put the clips on. Okay, so I let the amplifier discharge, and I connected onto the emitter resistors between Q11 and Q16. And if you look here, that should put us here and here. And a quick confidence check I do when I do that to make sure I'm tapped across them. They're 0.33 ohm resistors, so with the lead resistance 0.66, we should have around an ohm. And if I go over to ohms, you can see we got about 0.9. So it looks like I'm tapped off in the right place there. So now we can turn the amplifier on, and we have virtually no bias here. So let's see if we can rectify that. So I reach in. Yeah, so we do have adjustment here. Now I'm going to leave it on and calculate what it should be. I don't know if they tell you in the manual, but I can pop that up and we can take a quick look while that warms up. I don't see any smoke coming out of anything yet. All right, so I've looked through the manual. I don't see anywhere any specification for bias. So I'm going to have to calculate that, and my rule of thumb is anywhere between 20 and 30 milliamps. And we need to calculate what that is in millivolts. And to do that, we use Ohm's law. Specifically, we're going to use this formula here. We're solving for what kind of millivolts we want. So we take our desired current in milliamps times our resistance in ohms. So they're 0.33 ohm emitter resistors, so I'm going across both of them. It's 0.66. So for 20 milliamps, we're going to go 20 exponent -3 times 0.66. That gives us 13.2 millivolts for 20 milliamps of current. All right, if we want to calculate 30, we go 30 exponent -3. That gives us milliamps times 0.66. And our result is 19.8 millivolts. So anywhere between 13 and almost 20. So I've had this amp on for a couple of minutes. It's come up to about 1.7 millivolts. And I have had my hand in here tweaking this. And boy, the last quarter-inch of travel on this has an awful lot of difference. Barely moving this guy. And yeah, see, you really got to be careful. So okay, so anywhere between 13 and almost 20. So I'm going to leave it there for a few minutes. And meantime, I'm going to hook this up and we're going to put some signal through it and see what we get. I have the bias set to about 16 millivolts here, and I just want to raise the camera up so you can get a better look at the scope and the distortion analyzer. And when we put some signal on, we got both channels. Now, this is only a very small amount of signal going in. Let's see what a little more looks like, because that's a fraction of a watt. Just a little triggering issues there. 5 watts, I think it's 200 watts a channel. But in order to get that, I'm probably gonna have to run an extension cord because my bench power supply is already starting to sag a little. I'm running through the Variac, but I should have had dedicated 20 amp services pulled to my bench. I had my panel replaced and I should have done it then. I didn't. Okay, so That's about 40 watts a channel. Let's see. That's about 120. Yeah, I'm showing sag already, but both channels are working. So I'm going to pull a heavy extension cord out, run another outlet to the bench here, and I'll show you what we can get. Okay, so I've got a heavy extension cord. I think this might be a 12 gauge US wire code. But I plug in this guy so I can monitor voltage, current, wattage, and the amplifier plugs in here. I made this rig. There's a guy who goes by Arts, A-R-T-S, on a popular audio forum I used to belong to. He recommended one of these. I think it was $10 or $15 on Amazon. Excellent purchase. Highly recommend it. And Art, if you happen to see this, thank you so much. Really nice guy. I'm no longer active on that forum, but I should reach out to him just to see how he's doing because, as I said, really nice guy. Okay, so let's go back over and see what we can get this amp to do. I'm going to pause the camera just for a moment while I reorient. Okay, our bias is crept up to 17.5. So let's see if we can get 200 watts of channel out of this thing. That's what it's rated at. And let's see if we can get it to give up the goods. Okay, this is where we left off, 120 watts of channel. Okay. I can't see what I got going on here, but whoop, there we go. So that is 170 watts. Just starting to clip there. Starting to get some distortion on that one channel, on the right channel. Again, the way I'm measuring is not ideal. We aren't sagging too bad, pulling about 6.5, 6.6 amps. I am concerned about the amount of distortion on this channel. Okay, let me see if I can figure out what's going on here. Well, I guess it was time to RTFM because when I look in the manual, I found my mistake. This amplifier is rated at 150 watts a channel. It'll put out up to 190 at 1 kilohertz, which is where we are, but it's rated at 150 watts a channel. So if I turn it on here, we're getting about 170. We're at 1 kilohertz. Should be able to get a little more, but no more than 190. Okay, it is distorting a little more in the right channel, but yeah, at 190, I get about 1% on each channel. And it doesn't give you what the THD should be at that point. Let's see. Should put out less than 0.1%, but I am configured to measure power accurately. So here was a mistake I made for years. In order to measure power accurately, you need to measure at the load. In order to measure distortion accurately, you need to measure at the amp. So I made up some cables that would allow me to do that, and I'm going to pull those out. We'll reconnect this amplifier, and I'll see if the specs are any better. I don't think it's going to meet it, but I'll see if it's any better. Okay, I've got this reconfigured. Honestly, I don't see it making that much difference, but let's see what we get now. Still 1 to 1.6%. Again, we're over 190. Let me drop this down a little. Okay, this is still a little above spec, but on the other hand, the channel is working, and we're still a little above here, a little below here. I'd signed this video up, but I thought it might not be a bad idea to take a moment and talk about the different cables I use on the distortion analyzer, and also to point out a mistake I had made reading the specs. This amplifier does meet specs, and I'll show you that after I show you this. When I'm normally measuring amplifier output power, I just plug in this straight set of cables here, right? Just bananas, dual bananas on each end, and I plug into, always go left to right, red is right, and I just plug these directly into the amplifier's outputs. And the back of the dummy loads are connected right to these BNC cables that go into the input of the distortion analyzer. So we stimulate the amplifier with the oscillator output from the distortion analyzer. The output of the amplifier feeds the dummy loads, and tapped to the back of that are these. And that's good for measuring accurate output power. However, not that long ago, I was schooled that if you want to measure accurate distortion, you need to measure at the amplifier's output, not at the dummy loads. Accurate power measured from here, accurate distortion measured from here. And the reason for this is we don't have superconductors yet. There's going to be a little loss in the wires. So what I did was I made a different set of cables. These go to the dummy loads. These, however, go to the amplifier, and tapped off of each one of these is a BNC. And what I do with these is I put this into the amplifier, and then I take these off, and these go right to here. Now we're measuring at the amplifier's output and not at the dummy loads. So that's the deal with that. The other thing I want to point out is the mistake I made reading the specs. And as usual, it's the fine print that gets you every time. I was looking at this table here for the 6260, which is what this amplifier is. Mid-band power at 1 kilohertz, we should be able to get 190 watts. And it said distortion should be 0.1% for 8 ohm stereo. However, if you look underneath where it says mid-band power, maximum output power at onset of clipping, both channels driven with 1 kilohertz sine wave, THD 1%. So this amplifier does meet spec. Mistake was mine. I should have read the whole thing. The details get me every single time. Anyhow, as always, I thank everyone for watching, and I like giving back to the community that's given me so much. Thanks a lot, everybody.